Welcome to my channel. Today we are talking about signal state management in Flutter. Imagine you have a complex Flutter widget tree with dozens of nested levels. You want to update a single text label at the very bottom when a user clicks a button. In standard Flutter, using a typical change notifier or provider, updating that one value often triggers a rebuild of the entire parent subtree. Every single widget from the ancestor down evaluates its build method again, wasting CPU cycles and memory. What if we could target just that single text node and update it directly, bypassing the rest of the widget tree completely? This is where signals come in. Borrowed from frameworks like Solid.js and adapted for Dart, a signal is a wrapper around a value that automatically tracks its subscribers. Unlike a stream, which requires explicit subscription management and boilerplate, a signal knows exactly who is reading its value at any given moment. When the value of a signal changes, it doesn't broadcast blindly. Instead, it surgically updates only the specific computations and UI nodes that directly depend on it. No manual listener cleanup, no unnecessary garbage collection overhead. The signals pattern relies on three core primitives. First, we have the signal itself, the writable value container. Second, we have computed signals, which are read-only values derived from other signals. They cache their results and only recalculate if their dependencies change. Third, we have effects, which run side effects like API calls or disk writes whenever a dependency updates. Under the hood, a dynamic dependency graph is constructed automatically during execution, ensuring that updates propagate in topological order with zero redundant evaluations. Let's look at how elegant the code actually is. We declare a counter signal by simply writing signal 0. To create a computed value that derives from this counter, say checking if it is even, we use computed parentheses counter.value%2 equals 0. Notice how we don't declare any dependency lists. The computed function automatically detects that it accessed counter.value during its execution and registers counter as a dependency. If we create an effect that prints this value, it will execute automatically the instant counter.value changes. To bring this into Flutter, we use the Flutter_signals package, which introduces extensions like the .watch helper. When you call counter.watch context inside a build method, it registers the current element as a listener. When the counter value changes, only that specific widget's element is marked dirty and rebuilt. For even finer control, we can wrap our widgets in a watch widget or use signal widget directly. This localizes the rebuild to a tiny, isolated leaf node of the widget tree, leaving the rest of the layout untouched. Let's visually compare how this behaves compared to a standard state management tool. With inherited widget or provider, updating our counterlights lights up the entire screen's rebuild visualizer in red, showing dozens of widgets repainting. With signals, only the tiny boundary around the text widget lights up. This structural isolation is incredibly powerful on lower-end mobile devices, where layout calculation and widget rebuilds are the primary causes of dropped frames and stuttering UI interactions. Because signals are pure Dart objects with no dependency on build context, your business logic becomes completely decoupled from Flutter. You can test your entire application state, including complex computed chains and async effects, in pure Dart unit tests without mocking the widget tree or using widget testers. Signals gives us the declarative, reactive programming model of modern web frameworks while retaining the robust, high-performance rendering capabilities of Flutter. Thank you for watching this video. Please subscribe and follow.